Imagine writing like an elegant, perfectly optimized algorithm. You push your code, you spin up a container in the cloud, and it just runs.
Right, it's seamless.
Yeah, but then imagine realizing that to actually execute that code at scale, you need the electrical output of a medium-sized city
Oh, wow.
and a $1 billion hardware cluster just to prevent the whole system from crashing under its own weight.
Yeah, that's the reality check.
It really is. Welcome to the physical reality of frontier artificial intelligence. If you're tuning in tonight, maybe you're a software engineer compiling code, debugging a deployment, or just, living in that comfortable world of beautiful abstractions.
It is a comfortable world.
We are so used to the physical hardware being someone else's problem.
I mean, the cloud is a very comforting illusion and implies something weightless.
Yeah.
Right, like it's entirely detached from the heavy, messy reality of thermodynamics and silicon.
Exactly.
But the moment you step into the architecture of modern AI models, those abstraction layers just evaporate. You are suddenly staring at raw metal, and you're bound by cold, hard physics.
Okay, let's unpack this. Tonight, we are bridging that gap. We're doing a deep dive into a massive stack of notes on AI training infrastructure.
Yeah, there's a lot to cover here.
We're talking GPUs, high bandwidth memory, and the colossal clusters powering this current boom. And the central irony of the AI revolution is that it isn't just about elegant math.
No, not at all.
It's a story dictated by strict hardware constraints. So to really grasp what is happening in those data centers, we have to start at the core engine. And as software engineers, we kind of have to throw out a lot of our baseline assumptions.
You really do have to pivot your mental model. I mean, if you spend your day writing standard web applications, you rely heavily on the architecture of a CPU.
Right, which we're all super familiar with.
Exactly. A CPU is optimized for complex sequential logic. It executes highly unpredictable branching, like if statements, database queries, routing protocols.
Doing all of that incredibly fast.
Right, incredibly fast on a handful of really complex cores. But neural networks do not care about complex branching logic.
They really don't.
At its foundation, a neural network is just a relentless, staggering volume of linear algebra. It's matrix multiplication stacked on top of matrix multiplication.
Which requires an entirely different processing paradigm. We aren't doing the high-precision 64-bit floating point math you'd see in, like, scientific weather simulation.
No, you'd never get the throughput.
Right. In AI training, we are dropping down to 16-bit or even 8-bit floating point precision just to maximize that throughput. We're relying on SIMD, right? Single instruction, multiple data.
Which is exactly the architecture that graphics processing units, GPUs, were built for decades ago.
It's crazy how that worked out. Think about like rendering a massive video game world. Instead of calculating millions of pixels on a screen simultaneously, we're calculating millions of weights in a neural network.
That's a great way to look at it. The
And-
architectural overlap is just one of the most fortunate accidents in computing history.
For sure.
I mean, think about what a GPU was originally engineered to do. It renders millions of pixels, 60 times a second. The color of a pixel in the top left corner of your monitor doesn't rely on the logic for the pixel in the bottom right.
Right, they're completely independent calculations.
Exactly. So you need thousands of tiny, relatively simple cores calculating shading and geometry all at the same time. And neural network training shares that exact mathematical property.
Because during the forward and backward passes, calculating one weight update in a massive tensor can happen independently of the others.
Yeah, you're mapping a massive matrix of weights against an input vector. You're basically calculating the physics of light scattering across polygons, but repurposed to calculate the probability of the next token in a sequence.
And the hardware was just sitting there perfectly primed for this. Like, we see modern GPUs packed with tensor cores now.
Yeah, specifically designed for this.
Right, designed to execute fused multiply-add operations, which is the exact operation needed for neural networks in a single clock cycle.
And the sheer volume of that parallel math is what breaks traditional computing architecture. The compute speed of these modern tensor cores is staggering.
They really is.
They crunch numbers so fast that the processor itself actually ceases to be the bottleneck.
Which totally shifts the entire engineering challenge, because if the cores are that incredibly fast at parallel math, what is actually dictating the speed of a training run?
Right, that's the big question.
And the notes are very clear on this. The primary bottleneck in AI training is not compute. It is memory bandwidth, specifically high bandwidth memory, or HBM.
What's fascinating here is the physical mechanism. Let's visualize it. Imagine your thousands of GPU compute cores are robotic arms on an assembly line.
Okay, robotic arms.
They can assemble products instantaneously. High bandwidth memory is the conveyor belt delivering the parts to those robotic
A
arms.
bit.
If the conveyor belt cannot move fast enough to supply the data, the robotic arms just sit there idling.
Which is obviously terrible for efficiency.
Exactly. It's a state known as data starvation. The compute cores are literally just waiting for electrons to physically travel from the memory chips to the processing die.
Okay, and to understand why that conveyor belt is under so much strain, we really have to look at what actually has to live in that memory simultaneously during a training loop.
It's a lot more than you think.
Yeah, it's not just the model weights. If we take a standard large language model, say 100 billion parameters, you might think, okay, I just need enough memory to hold 100 billion numbers.
If only it were that simple.
Right. But the training state requires so much more than that.
The optimizer state alone is massive. If you're using a standard optimizer like Atom, which is incredibly common, Atom maintains a moving average of the gradient
Right.
and a moving average of the squared gradient for every single parameter in the model.
So it's tracking all of that history.
Yeah. So if you are training in 32-bit precision, you need 4 bytes for the weight, 4 bytes for the gradient, 4 bytes for the first momentum, and 4 bytes for the second momentum.
Okay, so that's 16 bytes per parameter.
Exactly. So your 100 billion parameter model suddenly demands 1.6 terabytes of memory just to exist in a trainable state.
Wow. And then you have to add in the activations, right? The
Yeah.
intermediate outputs from every layer during the forward pass.
Oh yeah, you absolutely must save those in memory so you can calculate the gradients during the backward pass. The memory footprint just explodes.
And every single piece of that data has to be accessible to the compute cores with basically zero latency.
Near zero, yeah. It has to be immediate.
Well, let me push back on this, or at least put on my traditional software engineering hat for a second.
Filter for it.
In normal enterprise backends, if my Redis cache overflows, I just hit the database. If the server's RAM fills up, the operating system just pages to the NVMe drive.
Right, standard practice.
Yeah, I just optimized the query to stream data in chunks. Why can't we just stream these weights and activations over, like, a PCIe bus from a massive, super-fast enterprise SSD?
I mean, that instinct makes perfect sense for web architecture. But it fundamentally breaks down in deep learning.
Because of the latency.
Exactly, the latency penalties. Let's go back to our assembly line analogy.
Yeah.
High bandwidth memory is stacked directly on the same silicon package as the processor.
So it's physically right next to it.
Right, it delivers bandwidth upwards of 3 terabytes per second. A high-end PCIe Gen 5 bus, on the other hand, might give you, 64 gigabytes per second?
Which is fast for a web server, but slow for this.
Paging to an SSD from the GPU is the equivalent of that robotic arm having to drive a forklift to a warehouse 3 towns over for every single screw.
Wow. And the compute cores are just dead in the water waiting for it.
Completely dead. And remember, you are updating these weights millions of times during a training run. A latency penalty of a few milliseconds per operation multiplied across billions of parameters.
Just ruins the math.
It ruins the whole timeline. A training run that should take a month theoretically takes 5 years. You just cannot fake memory bandwidth. You either have the data physically residing in the HBM attached to the die, or you cannot train the model efficiently.
But putting 80 to 192 gigabytes of HBM on a single die creates a literal physical ceiling, right? Like you hit the reticle limit of photolithography.
You literally do.
You physically cannot print a larger silicon chip with today's manufacturing tools. And you can't just stack more memory chips on top of each other.
No, because that creates thermal densities that will literally melt the processor.
Which is terrifying to think about.
You reach the absolute limits of material science. You can't cool it, and you can't manufacture it, which means a frontier model requiring terabytes of memory just for the optimizer states and activations cannot physically fit on one GPU.
You can't even fit on 10.
No, not even close.
Here's where it gets really interesting. Because that thermal and physical ceiling forces a massive paradigm shift. Since we cannot scale vertically on a single chip, we're forced to scale out horizontally.
They go wide.
Exactly.
Wow.
We transition from the micro constraints of nanometers to the macro constraints of massive data centers. We're talking about connecting 10,000, sometimes 20,000 GPUs to train a single frontier model.
It's mind-boggling scale.
And the economics of this transition are completely alien to traditional software development. Like the barrier to entry skyrockets.
Oh, absolutely. The sources note that training a true state-of-the-art frontier model today Costs between $100 million and $1 billion in capital expenditure.
Just for the hardware.
Yeah, and these aren't consumer graphics cards you can buy online. These are enterprise-grade accelerators costing tens of thousands of dollars each.
This is such a radical departure from the mythology of the tech industry, you know?
It really is.
We all grew up with that ethos of the garage startup. You have a laptop, an internet connection, a clever algorithm, and you can disrupt an entire industry.
Build a billion-dollar app from a coffee shop.
Exactly. But in frontier AI, elegant code is just not enough. The cover charge just to run your code is $1 billion of iron.
And buying the GPUs is literally only the first step. When you split a single neural network across 10,000 GPUs, the communication overhead between those chips becomes the new bottleneck.
Because they have to talk to each other constantly.
Right. You have to synchronize those gradients across the entire cluster.
And the networking constraints there are brutal. We are talking about east-west traffic within the data center. You aren't using standard Ethernet switches here.
No, standard Ethernet would choke immediately.
You're building non-blocking InfiniBand topologies. The network interface cards alone are incredibly specialized, because if GPU number 1 needs to wait for GPU 9000 to send a gradient update.
The entire cluster stalls.
Exactly, it's a house of cards.
And the operational reality of a cluster that size is just a nightmare of probability. When you have 10,000 highly complex chips running at maximum thermal capacity, the mean time between failures drops to hours.
Oh man, so things are breaking constantly.
Inevitably. A single GPU will fail, a network link will drop, and when that happens, the training run halts. The engineering team has to isolate the dead node, load the massive terabyte-scale state from a checkpoint, and resume.
Which means checkpointing itself becomes a massive input-output bottleneck.
It's a huge operational drag.
And, you know, when an infrastructure requires this level of capital, custom networking, and sheer physical space, it fundamentally changes the nature of the business.
You're no software company anymore.
Right. You are an infrastructure operation. You are heavy industry. And that massive physical footprint brings us to the geopolitical realities highlighted in the sources.
Yeah, this is a crucial part of the deep dive.
The global supply chain for this hardware is a massive choke point.
If we connect this to the bigger picture,
Yeah.
it is arguably one of the most critical hardware supply chains in human history.
No exaggeration.
The intellectual property, the architecture of these advanced chips, is designed almost exclusively in the United States. But the physical manufacturing is hyper-concentrated. They are fabricated almost entirely in Taiwan.
Looking strictly at the facts outlined in the notes here, it really comes down to the foundries. Specifically, the advanced packaging technologies required to attach that critical high-bandwidth memory to the compute die.
Yeah, it's not just making the chip, it's packaging it.
Yeah. Right. Technologies like TSMC's CoWoS, chip-on-wafer-on-substrate, it's an ultra-complex silicon interposer that allows the memory and processor to communicate at those 3 terabyte per second bandwidths we talked about earlier.
And there are very few facilities on the planet capable of doing this at scale.
Exactly. The concentration of that manufacturing capability inherently makes it a geopolitical lever. Because the supply chain is so narrow, export controls actively dictate the landscape of global AI development.
The regulations govern exactly who is legally permitted to purchase these high-end accelerators and in what quantities.
And simply reporting the reality on the ground here without taking any stance on the policies themselves, these export controls functionally shape the future.
They absolutely do.
If you cannot secure the physical hardware, you cannot train the frontier model, period. A team of engineers could theoretically draft the most efficient, revolutionary neural network architecture on a whiteboard.
But without access to the silicon, it's nothing.
Yeah, without the advanced packaging from those specific foundries, it remains entirely theoretical. Software is completely subservient to the hardware supply chain.
It forces us to recognize that artificial intelligence is not some digital ether. It is grounded in trade routes, manufacturing yields, and physical logistics.
And real-world resources.
Exactly. And perhaps the most pressing physical constraint of all, one that the sources call the environmental elephant in the room, is the power consumption required to turn all of this on.
We mentioned at the top of the show, we aren't talking about plugging a few server racks into the municipal grid.
Not even close.
A 10,000 GPU cluster consumes tens of megawatts of power continuously. A single training run, which can last several months, can draw the electrical equivalent of a medium-sized city.
It's staggering.
You cannot pull that kind of energy from a standard grid without causing massive infrastructural and ecological strain.
And the sheer physics of that power draw acts as a massive forcing function within the industry. It is no longer just an environmental concern, it is a strict operational limit.
Right, you literally can't build it.
You cannot secure enough gigawatts of power in major metropolitan areas to build the next generation of data centers.
Which is driving these infrastructure companies to completely rethink their energy dependencies. We're seeing massive investments pivoting toward renewable and dedicated energy sources.
Yeah, tech giants are securing agreements to collocate data centers directly next to nuclear power plants.
Wait, really? Next to nuclear plant?
Oh, absolutely.
Yeah.
They are funding massive-scale solar arrays
Well,
and wind farms. And they aren't just doing this for, like, sustainability reports.
they're doing it out of a necessity.
Exactly.
Yeah.
They literally cannot secure the continuous baseline megawatts they need from the traditional grid to keep scaling these clusters. Brute force scaling is hitting the wall of physics.
And when scaling horizontally becomes this economically and ecologically expensive, efficiency suddenly becomes the most valuable currency in the industry.
It changes everything.
It drives the need for more specialized silicon, chips that can deliver more fuse multiply-add operations per watt of thermal design power.
And crucially, it drives the need for algorithmic efficiency. As a software engineer listening to this, you might not be laying fiber optic cables for an InfiniBand network.
Probably not.
Or designing silicon interposers in a Taiwanese foundry. But understanding these strict physical constraints is what allows you to write better architecture.
Exactly. Knowing that memory bandwidth, not compute speed, is the ultimate bottleneck completely changes how you structure your model's layers.
Oh, for sure.
Knowing the sheer cost of east-west network traffic changes how you approach parameter distribution.
You have to build software that respects the physics of the machine. The engineers who are going to define the next era of artificial intelligence are the ones who understand how to keep those thousands of compute cores perfectly fed with data.
Without bottlenecking the memory or saturating the network.
Exactly.
And that is exactly where we are heading next. Tomorrow, we are going to dive into the software side of this logistical nightmare.
The distributed training problem.
Yes. We've established today that a frontier model cannot fit on a single GPU. So tomorrow, we tackle the hardest engineering challenge in all of AI distributed training.
I'm going to do a deep one.
How exactly do you take a model with hundreds of billions of parameters, chop it up using tensor parallelism and pipeline parallelism, and spread it across 10,000 individual GPUs?
And keep them all perfectly synchronized.
Right, without the communication latency ruining the entire run. The math required to orchestrate that is just brilliant.
It really is an absolute symphony of parallel processing and network topology. Getting that right is the only way these massive clusters function.
So what does this all mean? We started by talking about the comfortable abstractions of traditional software engineering.
We ended up pretty far from that.
Yeah, we've ended up deep in the realities of thermal limits, silicon foundries, advanced packaging, and literally nuclear-powered data centers.
It leaves us with a critical tension. We've established that the physical realities, the thermal limits of high-bandwidth memory, the billions of dollars in capital requirements, the highly constrained supply chains, and that massive power draw, they strictly limit who can participate at the absolute cutting edge.
The barrier is incredibly high.
The moat around frontier AI right now is built out of massive hardware clusters. But this raises an important question to ponder as you log off tonight.
What's that?
Will the next true leap in artificial intelligence come from those few massive organizations that hold the keys to the hardware monopolies? Or, well, will it come from a single software engineer who figures out an algorithmic breakthrough so fundamentally efficient that it completely bypasses the need for 10,000 GPUs in the first place?
That is the ultimate question. We tend to assume the future belongs to whoever can string together the most megawatts and the most silicon.
Right.
But when you look at the sheer friction of scaling hardware, the landscape for software architecture is still incredibly vital. The physical constraints are real, but elegant code still has the potential to rewrite the math. Until tomorrow, keep building.